everyone. Today we're going to be talking about Route LLMs, learning to route LLMs with preference data. Basically, what this means is we want to route user queries to an LLM that is specifically trained to answer and output a good response specifically for that query. What are LLMs and understanding Route LLMs? LLMs are machine learning modules that comprehend and generate human text that can be used to perform simple administrative tasks. LLMs differ in training quality, size, access to training data, application, and costs, which in turn determines the speed, strength, and efficiency of the said module. Larger modules are more equipped with sufficient and quality data, which in turn increases its level of performance against smaller modules, which may not be afforded the same luxuries. However, the trade-off presents a huge difference in cost and maintenance. Router models exist to bridge this gap. A router model is designed to route queries to its most efficient model. For example, we train data using two modules such as ChatGPT and Mixtral 8x7b. Our LLM router acts as a mediator between user queries and the model. It sends complicated queries to GPT-4 and less complicated ones to Mixtral 8x7b. Next slide, please. Router modules exist to bridge this gap. A router module, for example, is designed to route queries to its most efficient module. For example, we train data using modules such as ChatGPT and Mixtral. This is done to maintain a balance of quality, accuracy, cost, and efficiency. So now we're going to be talking about the process of routing LLMs routing user queries from the client to LLMs. LLM routing creates a system that directs queries to either high-quality closed LLMs or cost-effective open-source LLMs based entirely on the complexity, response quality, and costs. So, for example, if we were to query an LLM, for example, we ask it, what is a Pythagoras theory? We expect our router to take this query to a less weaker module that's trained on less quality data and reduces costs. If we then say, we have this triangle, can you calculate the distance using Pythagoras theory? We would expect our router to take this query to a much more advanced LLM-based data, such as GPT-4. LLM routers are used to balance the query. Sorry, can you go back, please? LLM routers are used to balance the query routing, ensuring that they reach the intended module designed to handle the parameters of the query. An LLM module can be closed or open source. The challenges with routing is how we can achieve an optimal equilibrium between increasing response quality and reducing cost. Next slide, please. Now, we're going to talk about how we can formulate a problem around this. The routing function is based as an n-way classifier that selects an appropriate module based on the complexity of the query and the model's capabilities. So consider a set of n different LLM modules stored in a dictionary, such as the equation we've got here. The routing function is designed to take user queries and map out the queries to the most effective LLMs based on their complexity. As an n-way classifier, that takes a query of Q and gives an output and selects a model to answer the question. A successful LLM route function heavily depends on equilibrium between efficiency and costs. This research is particularly focused on binary routing between strong modules, such as high quality, and costs, such as GPT-4, and weaker modules such as Mixtral 8x7b, which have low quality and cost. We want to establish a framework for learning optimal function routing. Next slide, please. The principled framework for learning a binary routing function is presented as a component taken in a query, and we represent our weaker modules and our stronger modules as 0 and 1. 0 representing the weaker modules and 1 representing the strong module. Q representing the query, whilst RA bin represents the perfect equilibrium we want to figure out. To achieve this, we split our measurement into two components. Firstly, the win prediction model. This model predicts the probability of winning for strong modules, represented as M strong. In the binary classification, setting the algorithm captures a win-loss probability of both model classes. Learning the probability on preference data enables us to capture the strengths and weaknesses of both model classes on various kinds of queries. Our second component is the cost threshold model. This model converts the winning probability into a routing decision between M strong and M weak, represented as ones and zeros. We denote the router's response as this equation, which represents the response generated by either the weak or strong model, depending on the router's decision. Now, with metrics, we evaluate metrics to capture the trade-off between cost and quality in the LLM routing problem. The starting point is metrics that assess independence to quality and cost efficiency. We introduce compound metrics such as, for cost efficiency, we calculate the percentage of calls to the strong module against the weaker module. And for quality, we measure response quality on an evaluation set. To quantify the cost required to achieve a certain level of performance, we use a metric called Call Performance Threshold, CPT. Given a router's desired performance measured as PGR of X%, the CPT refers to the minimum percentage of calls to the strong module required to obtain the desired PGR. So I'll be handing over to my colleague Bharat Jawar to take you through the next slide.
Hi everyone, thank you Ajibola. That was well explained. Now that we know about what is LLM, what is LLM routing, how is our problem formulated, and how are we going to deal with it using win probability model and cost threshold model with the knowledge of key matrices we are going to use. Let's talk about the methodology. The methodology outlines the process of training a routing function for selecting between strong and weak language models using preference data. Meaning for a given query, there will be two responses generated and the person will choose between the one. This way we get the model which is preferred. Where is this happening? There's a platform, chatbot arena platform. There we are gonna give queries and the user is gonna say which response from which model is better and what is preferred. What is the dataset composition look like? It contains a query. It contains the answers for the query from the two models. And the very important thing, which is comparison label. This means like what is the based on the human judgment, obviously, like what is the how well is the comparison between the two models, which model is better than the other, by how much. Coming to the challenge faced while getting our data is label sparsity. For any two models, the percentage of direct comparison was less than 0.1%. This sparsity presents a significant challenge for training a robust routing function, as there are not enough direct comparison for most model pairs. So how do we address it? Firstly, there are 4 steps for addressing it. Clustering models into tiers. To reduce label sparsity, the authors cluster the models into different tiers based on the ELO ratings, just like how the skills of a player in a game of chess are ELO'd. And the second step would be to define strong and weak models. Models in top tier are considered as strong models, whereas the models in lower tier are considered to be the weak models. Training data construction. How is the data is being focused, trained? So it is primarily used battles between strong and weak models only. This improves the robustness of routing function. The fourth, but the very important step is to omit the model responses. We don't need everything. For example, we don't need the responses the model is generating. We just need the query and what is the comparison label. That's how we can omit the model response and get a better data for us. The data augmentation section describes the methods used to enhance the dataset for training the routing function, addressing the challenge of sparse human preference signals even after classifying models into tiers. The very first data augmentation would be the golden label dataset. The purpose of it is to augment the training data with more robust and reliable comparison labels derived from the dataset where the correct answer is already known to us. How does this work? For each question, responses from two different models are compared by evaluating how well they align with the golden label. That's why the name, the golden label datasets. The second is the LLM judge labeled dataset. The purpose of it is to get the purpose driven chat domains by leveraging a large language model as a judge, which can mimic human judgment with high accuracy. There is a main challenge during the LLM judge label dataset, which is its high cost associated with it, especially when you are using ChatGPT 4 as your judge. But how to fix it? Instead of generating all responses from scratch, the author select queries that already have GPT-4 responses in it. Then they generate the additional responses using a weak model such as Mistral 8x7b and obtain the comparison labels using GPT-4. This helps reduce the cost by a lot. Now that we know about the training data, the data set we are going to work upon, let's talk about the routing approaches. So the very first routing approach is similarity weighted ranking. This method is based on Bradley-Perry model. The core idea of similarity weighted ranking is to weigh models based on their similarity to each other or to specific query and then rank them accordingly. The first equation is for weight calculation. It is the similarity equation, which is using the cosine similarity between queries. The second equation is the binary entropy loss calculation. It is calculated by minimizing the weighted binary cross entropy. The third equation is the win probability estimation, which will help demonstrate the model. The second routing approach is matrix factorization. This is inspired by a recommendation system. Matrix factorization helps predict which model would perform best for a given query by learning latent relationships between queries and models. Like learning relationships between queries and models. So the key concept is to predict a score that represents how well a particular model will respond to a specific query. So the next, okay, so this is divided, and there are three components for it. The first component is scoring function, the second component is win probability, and the third component is billionaire scoring functions. The third important routing approach we took is the BERT classifier. By using BERT in a routing approach, the system can leverage its deep language understanding to effectively categorize the direct text inputs, enhancing the efficiency and accuracy of automated response or workflow. Here we use a BERT-based architecture to embed the user query and predicts the win probability using a logistic regression head. Here is the win probability is how it is defined. The equation is given. The HCLS is the embedding corresponding to the special classification token that summarizes the input query. The others are just the parameters for the logistic regression head in the BERT model. The fourth and the last approach for LLM routing is casual LLM classifier. This approach leverages Llama 3.8b and follows an instruction following paradigm where the model is prompted with the user query and predicts the win probability for which model is going to win. So now that we know about the routing approaches, we know about the key matrices, let's just see how the experiments are going to go and what are the results. There are three evaluation benchmarks for it. The very first evaluation benchmark is MMLU, Massive Multitask Language Understanding. This consists of 14,000 questions, a multiple choice question, you can say. And the second data set would be Empty Bench, that includes 160 open-ended questions. The third data set would be GSM8K, which comprises over 1,000 grade school math problems. These are the evaluation benchmark we have set. Now let's talk about the results. As we know, Ajibola talked about the CPT with X percentage. So we are going to take it to 50% and 80%, and also going to find the average probability of getting it right. So CPT discusses about the accuracy of the routers, whereas APGR measures the average probability that the router selects the correct model. So let's just see how to read these results for the MTech bench. The random router performs at 49.03% when the CPT is at a threshold of 50%, and 78.08% when the CPT has a threshold of 80%, and the APGR is of 0.5. Let's talk about how did it perform, how the four routing approaches worked on the D-Arena training datasets. BERT shows the highest performance with CPT 50% and CPT 80%, but the APGR is very low than the random router. It's less than 20%. It's less than 20%, which is minus 21.8%. The casual LLM also performs well, but like BERT, its APGR is just a bit above the random router. Then comes the matrix factorization and SW ranking. Performs significantly worse in CPT 50%, but its APGR is very high than the random baseline. And similarly, the SW ranking as well. So now let's talk about when we mix the dataset of the Arena platform and the golden judge and the golden label judgment. So BERT and casual LLM perform poorly in terms of CPT 50%, indicating that adding the judge data makes these methods worse in low data regimes. But we can see matrix factorization and SW ranking show significant improvement when the data judge is added, especially in terms of APGR, average performance. So like each and every responses are way better. So in conclusion, for the results of empty bench, we can say that the matrix factorization and SW ranking are more robust method, especially in scenarios where additional judgment data is available. Similarly, there are results for these are the points I have jotted down. Similarly, there are results for MMLU. In MMLU, similar to empty bench, the matrix factorization and SW ranking works better when it comes to D-Arena platform. And when it comes to D-Arena and gold then dataset, the casual LLM and the SW ranking performs better. And when we talk about the results for GSM8K, in the D-Arena, similarly to MP bench, the matrix factorization and SW ranking works better. But when it comes to D-Arena and the judgment LLM judge dataset, the casual LLM performs better. This just goes to say that when we are talking about GSM8K dataset, which consisted of the school math problems, the casual LLM can solve it way better than the other four routing approaches. Whereas when it comes to open-ended questions or multiple choice questions, matrix factorization and SW ranking routing functions are much better. So what was the purpose of our LLM routing? It was to minimize the cost and to not affect the quality of our responses. So how did we do it? So after measuring it on our evaluation benchmark, we find that we have saved up to 3.66 times of the total cost that it was already been given. In conclusion, we can say that the research on LLM routing is a success as we have lowered the cost and also upheld the quality of our responses from the models. Thank you. That was our time. If you have any question, there's a link for the paper. You can go ahead. Thank you everyone for joining in.
Yeah, see you.
Bye.